Okay, so we have concluded the book, basically, including the radiation by accelerated charges. You see, what we did was not really the we considered the electric field of a moving charge. We considered the dipole. And we looked at the radiation by a dipole. Now, for a point charge, you can say that the point charge has an electric dipole moment given by Q times R of t. Well, since we know what is the radiation by a time-changing electric dipole, so we already have described that motion. Well, there is one thing that I would like to discuss if you don't have something else in your mind. If you remember, in our first year, we also described the acceleration by a moving charge, the radiation by an accelerated charge. Do you remember it? You see, the first year books, your first year general physics book, basically gives you the physical intuition without going into the mathematics. This course, here our aim is more like, how do we describe it mathematically? But sometimes the danger is that the physical picture is lost in this mathematical description. So I strongly suggest you to keep your freshman books for your at least 4 years and keep it as a reference book for whatever you study. There is a discussion, there is a chapter in your freshman book. Now, in that freshman year, what we were doing is something that we had also obtained over here. If you have a charge that is moving at constant velocity, the electric field lines are still radially outward. So what we will imagine first is that the velocity of the acceleration of my particle as a function of time will be this one. It's A if t is between 0 and tau, 0 otherwise. And again, for simplicity, I will just consider a system that is at rest to start with. Or you can say that I'm in a reference frame in which the particle is at rest at t is equal to 0. I can always choose such a reference frame. Since before t is equal to 0, it's moving at constant velocity, I can always go to a reference frame which moves with that constant velocity, and in that new reference frame, it will be at rest. And then I look at what happens at the time t. So basically, my particle starts here, then accelerates for a very short amount of time. This is the acceleration region. And then it keeps moving with constant velocity after that time. And currently, this is at t is equal to 0. This is at t is equal to tau. This is at t much larger than tau. Now, what do we know? Basically, all the changes, they move at the speed of light. Now, there are some electric field lines that started from this point, and they have moved at the time t. In a given time t, let's say, they would have moved up to this circle. Let's say the radius is c times t. Now, any point out of this region doesn't yet know about this acceleration. The particle was at rest to start with. So the electric field lines were just radially outward. And out of this sphere, the electric field lines will still be radially outward, because they didn't yet feel the acceleration. Now, after this point, it's moving with constant velocity. For an amount of time t minus tau, it just moves with constant velocity, so all the electric field lines are moving with it with the same velocity. The electric field lines will still be radial. So around this point, there is another sphere. Within this sphere, the electric field lines are still radially out. Now, the problem is what happens in between. So that's the question. Well, Gauss's law tells us that the electric field lines cannot terminate, they cannot start. That also tells me that the electric field lines cannot be broken. They have to be continuous, unless there are some charges in a given region. Let's look at this region. There are no charges there, it's vacuum, it's empty space. So the electric field lines cannot just break like that. And if it were to break, it would mean this electric field line just terminates over here. But it just cannot be. So what happens is the electric field lines inside this smaller sphere should somehow connect to the electric field lines outside my sphere. And assuming that this tau is short enough, whatever the shape is, it will be almost a straight line. Whatever your curve is, if you look at a sufficiently small segment, it is straight in that segment. So this will be my electric field lines. So, you see, it is continuous. Actually, of course, it will not be so, there won't be such a sharp point. It will be a smooth transition. It bends. But that smooth transition, I can always approximate it by a straight line. Yes. You see, the electric field lines within the smaller sphere, they are created after the acceleration when my object is moving at constant velocity. The electric field lines out of this larger sphere, they were created before my particle started accelerating. So it was at rest, or you can say that it was also moving at constant velocity. What happens in between is due to what happens during this period where my particle is accelerating. And whatever happens during that time should somehow connect the electric field lines in the inner sphere to the electric field lines to the out of the outer sphere. Now you see the direction of the electric field line gives me the direction of the electric field. So in that region, in this region, this is the direction of the electric field. Let's look at this angle over here. Tangent of that angle will be this component of the electric field, that is the tangential component of the electric field, to the radial component of the electric field. Well, let me give it a different name. I will call theta something else. Let me call that alpha. So the tangential component of the electric field is nothing but the radial component of the electric field times tangent alpha. Now, what about the radial component of the electric field? Well, let's see. I know the radial component of the electric field over here. It is just 1 over 4 pi epsilon 0 q over this distance squared. I also know what the radial component of the electric field over there is. It is again just q over 4 pi epsilon 0 q over this distance squared. Well, this distance squared and this distance squared, since I'm considering t much, much larger than this tau, I mean, we are talking about kilometers, let's say, kilometers away. And this separation over here, let's say, is centimeters away, centimeters long. Tau is very small, that's what I will be assuming. Now, this distance and this distance, they are basically the same. There's nothing really changes. Well, the radial component will be continuous. So it will change from this value to this value in this region. But the value here and the value over there, they are more or less the same. So the radial component doesn't really change. We know what the radial value is. This is equal to q over 4 pi epsilon 0, 1 over r squared tangent alpha. And this r, as you like, you can take that either to be this length or anything in between. They are basically the same. Yes? You see, that is a region where it is accelerating. In this region, it is moving at constant velocity. In this region also, it's also well, you see, the particle is at constant velocity, accelerating constant velocity. So just think of it like this. You have we don't have a long enough spring, but let's say you had a long enough string, you hold it over here, and then let's say you shift it up. It's tense. So if you shift it up, what will happen is there will be this deformation that will propagate as a wave. When it reaches a region, that region will go up and stay up because I just shifted up. So what will happen, the shape of the string at some later time will be flat over here because my hand is now up. And then it will go down and flat over here. This is what's happening over here. Just think of these electric field lines as string. You just shift it up due to this acceleration over here.
The bigger sphere is for when the charge is at rest. And the smaller sphere is for when the charge is moving.
Yes.
So what is the smaller sphere smaller than? Why should it be smaller?
You see, let's again repeat what I'm doing. The time scale that I'm considering. I'm at rest. There are electric field lines everywhere, radially outward from my rest position. Then at a given t equal to 0, I just start moving at constant velocity. Now I first accelerate with some possibly large acceleration, and then I start moving at constant acceleration. Certain things have been changing. My position is changing, my velocity is changing. But that information, we have seen that it propagates outward at the speed of light. For example, when I was here, when I start moving, you realize that I'm moving at a later time that I started moving, at a time our distance divided by c. So if I'm at the time t, much larger than the period in which I accelerated, let's say, at a time t, that information that my charge has accelerated could have traveled at most a distance c times t. Okay, so this is why out of this sphere of radius c times t, nothing has changed yet. They will change eventually, but not yet. Thanks at this time t, I have been moving with constant velocity for a time t minus tau. So the radius of that small sphere, let's call that r prime. This r prime is c times t minus tau. Because I have been moving at constant velocity for a length, for a time t minus tau. That information had propagated only a distance c times t minus tau. And that distance is definitely less than c times t. That's the small and the large sphere. So the question is, how do I connect this smaller sphere to the outer sphere? That is how the electric field changes due to this acceleration. That bend is due to the acceleration of the charge. And here what I'm assuming is I already know what happens to my charges if they are moving at constant velocity. I don't know what happens when my charges are accelerating. So I can kind of try to eliminate the region which is determined by what happens when the charge is accelerating. So I know what happens inside my smaller sphere. I know what happens outside my larger sphere. I don't know what happens in between due to this acceleration. But whatever is happening, keep in mind that this shell is very small compared to the radius. It's a very thin shell. It's not spherical shell. I mean, this side is thicker than this side, for example. But nevertheless, it is very thin. So whatever is happening in this region, so there will be some line connecting this radial line to that radial line. There will be some curve. Whatever that curve is, it can be bent like this, bent like this. I don't really care. It's for a sufficient, since that distance is sufficiently small, it will be almost flat. Almost, not exactly, but almost.
Hocam peki bu içteki sferi belli bir süre sonra yakalar mı?
You see, look at there. What is the distance between the radii? Can it be larger than 0, smaller than 0? Can this distance go to 0? What is this distance? You see, that distance, if you are interested in, let's call that d. D would be r minus r prime minus almost a times tau times t minus tau. Because it's moving with this constant velocity for a time t minus tau. This will be all, you can show that this is always larger than 0. Anyway, that's kind of a side discussion. What we are interested in is what is happening over here.
The radial electric field lines are not in specific lines. I mean, they are very crowded, and
Sure.
there are some kind of continuous. So
Sure.
alpha should be very, very small.
Well, you see, you're right, electric field lines are continuous, almost continuous, but I'm picking one of them. And I know that that line moving in that, making that such an angle, will start with along this line in the inner sphere, and it should go along that line on the outer sphere. And it should match. Well, you see, alpha, now we will calculate alpha. Alpha is determined by my acceleration, and for how long I have been, well, it will be mainly determined by my acceleration. Without acceleration, alpha would be 0. It is not determined by how dense my electric field lines are, because I'm just picking up one electric field line. And I'm trying to see how it just bends in this region.
But for example, we can choose an electric field line of outer sphere closer to the inner sphere. I mean,
What do you mean
in order
closer?
not to have that much angle, they may be closer.
We will see. I mean, that alpha will, of course, will also depend on this angle over there, which I will call theta. I will calculate alpha as a function of theta, and we will see how alpha changes as I change theta. You see, there's no bending over here. So that's basically why we don't have a radial radiation in the direction of acceleration. Or there is no bending over here. That's again is why we don't have any radiation just in the opposite direction of acceleration. The maximum bending will be in the perpendicular direction. Sure. Well, you see here, well, not that much, but this is what I will obtain at the top. This is what I will have over here. This is what I will have over here, etc. I just pick one of them. Now let's see what is this tangent alpha. On one hand, I know that tangent alpha is the tangential component of the electric field divided by the radial component of the electric field. On the other hand, tangent alpha is, let's call this distance A, this distance B. Tangent alpha is just A over B. Now we can calculate this A and B just from geometry. You see, my particle started here. It moved up to this point. This is what I call A. A is nothing but, let's say, it moves a distance L during this time. A is, or A over L is just sine theta.
Hocam o küçük kırmızı nokta da o eğrimin içinde mi yoksa?
Well, that is, it doesn't really matter. That is such a small distance. So this tells me that A is equal to L times sine theta. What is B? Well, B is basically the diff R minus R prime. So a tangent alpha L times sine theta divided by C times tau. So let's see, what is the tangential component of the electric field? You see, it was just Q over 4 pi epsilon 0, 1 over R squared, tangent alpha, which is L sine theta over C times tau. Now let's try to simplify it a bit. Q over 4 pi epsilon 0, 1 over R squared. Well, L is basically V times T, well, if you like T minus tau, well, V times T, let's say, more or less, times sine theta over c tau. You see, v is the velocity speed of my object. Tau is the time in which it accelerates up to this speed v. So v over tau is nothing but the acceleration. Well, we are looking at the point R. You see, we are considering the tangential electric field at this point, at a distance r, from whichever you would like to call the origin. But r is nothing but c times t. Or t is equal to r over c. So the tangential component of the electric field is q over 4 pi epsilon 0, 1 over r squared, a times r over c squared, sine theta. Well, these r's I can cancel, so what I end up having is q over 4 pi epsilon 0, a 1 over c squared is just mu 0 epsilon 0, sine theta over r. Epsilon zeros I can cancel. This is mu 0 over 4 pi, q times a, sine theta over r. Well, q times a, by the way, this a is not the a at the time t. That is the a acceleration at the time t minus r over c. Retarded time. Basically, you see what happens over here. The acceleration is at the time 0. I'm looking at the acceleration at the time 0. A is the acceleration of the object at the time 0, or between 0 and tau. And now I'm looking at the electric field at a later time t. So that A over there, that appears over here, is not A at the time t, it is A at the time 0. And 0 is nothing but t minus r over c. Okay, so let's see. This q times a, I can write it as q times d squared r by dt squared. This is d squared by dt squared of q times r. This is nothing but d squared by dt squared of p double dot. Well, we are back to the expression we had in the lecture. So the tangential component of the electric field is mu 0 over 4 pi p double dot sine theta over r. Well, this is the tangential is tangential to the radial component. So if you are looking at this point, the tangential component is this way. Now the question is, what does tell me that this is a radiation field? There's this additional electric field, not just the radial component, there's the tangential component. Whether you call it the phi or theta hat, it's, well, up to you. What tells me that this is a radiation field? I will say that this is a radiation field. This is the radiation by accelerated charges. What tells me that this is a radiation field? No. No, neither the sine theta. You see, it is this 1 over r. You see, electric field goes as 1 over r. If you calculate the corresponding magnetic field, it will also go as 1 over r. So the Poynting vector will go as 1 over r squared. So if you integrate it over a sphere at infinity, you get a finite number. It doesn't go to 0. The total energy passing through a surface at infinity is not 0. There will be some energy that passes through it eventually. So that is what we call a radiation field.
Yani bu ET'nin tamamı radiation.
Yes.
Ama biz bunun aynısını ya parçacık sabit hızlıyken bulmuştuk.
No.
Aynı terim değil mi?
No. You see, if you look at the expression of the electric field for a particle moving at constant velocity, you get 1 over some distance squared, not 1 over the distance. So whenever you have this distance squared terms, etc., they cannot go to infinity. They are attached to your particle or your charge.
Peki hocam biz buna X ışını diyebilir miyiz? Yani X ışında
What do you mean by X radiation?
elektron işte ivme kazanıyor. Sonra onu yavaşlattığımızda
That is not how you define the X radiation. X radiation is a radiation with a particular frequency. This tells you how you can create it. You see, well, let's go back. Or with a particular energy. What should be the acceleration of the charges if you want to calculate the X radiation? You first need to obtain what should be the electric field corresponding to X radiation, and hence what is the corresponding acceleration of the charges. The mechanism of creating X radiation is exactly the same. You just take electrons, you hit them on some metal, you basically cause them to accelerate. You send them high energetic electrons, they stop, more or less. Well, that's a huge acceleration. So they will radiate. And they will radiate at a particular frequency which corresponds to X radiation. In fact, whatever kind of radiation you have, this is more or less how you create it.
gamma radiation.
Exactly, like this way. But of course, in that case, the amount of the necessary frequency, you can only oscillate something with that frequency if it is smaller than the nuclear size. So it's the acceleration of the charges within the nuclei that is creating gamma radiation. Well, of course, in that case, you have to add the quantum mechanical description, etc. But even the quantum mechanical description, the basic idea is exactly the same. Wherever you see acceleration, here you have to put in some expectation value of the acceleration operator, if you like.
O zaman sadece bir elektrondan da gamma ışını elde edilebilir.
Sure. That's called a free electron laser. You see, acceleration happens on my point particle only at this point. This region is the electromagnetic field created by my particle while it was accelerating. This is the region where the electric field is created while my particle was at rest. This is the region in which the electromagnetic field in this region is created by my particle while it was moving at constant velocity, and this is the region in which the electromagnetic field was created while my particle was accelerating. The acceleration only happens here for my point charge. There's no other acceleration I'm talking about. Sure, but you see, the results we derive are valid with these assumptions. If you want to be more precise, you should look up what we had derived before. Even there we have certain assumptions. If those assumptions are not realized, then that final result will not be valid. So you have to work out what the result will be, provided your circumstances. No? You see electromagnetic wave, okay. Electromagnetic waves, what do you mean by electromagnetic waves? Electromagnetic radiation waves? Well, you see, I take my charge, I cause it to oscillate up and down. There is the radial component. The radial component oscillates up and down. It's not the radiation field, though. There's a wave over there, which is not radiation. It is attached to my charges. It doesn't go to infinity. I won't feel anything at infinity due to this radial component. I oscillate it. There is this tangential component, which can go up to infinity. The thing is, you cannot create radiation, whatever its form is, without acceleration. Basically, by definition. You can create electromagnetic fields without radiation. Just consider a point charge moving at constant velocity. No radiation, but there's still an electric field, there's a magnetic field. No. But just oscillate it slowly. There's almost no radiation. Still, the radial component of the electric field will have a wave. It won't go up to infinity, but nevertheless, it is still a wave.
Peki hocam, bu oscillation zamanla böyle hızlansa?
Fine, no problem. These are the results.
Ve o frekans değişen.
Sure. I mean, you see, there are certain assumptions we made over here. As long as you don't break those assumptions, these results will hold. Well, you want a general derivation, that we had already done in the book. And those assumptions were basically based on various distances we were considering. As long as you don't break those assumptions, those results are valid. You can consider whichever complicated motion you can think of. The question is, do you break those assumptions or not? If not, those results are valid. If you do, well, you have to work it out.
Hocam biz bir de şey demiştik yani, işte parçacık hareket etmeye başladığında elektrik alanlar işte bükülüyor. Ama burada her seferinde...
We are assuming they are moving slowly. You see, we made that assumption that they are moving slowly at this step when we said ER is equal to this one. So at that step, we are assuming that it is moving slowly. But it doesn't really make any difference. You see, if it's not moving slowly, just take that expression of ER and put it over there. But basically, if you do that, that kind of makes the main motivation in this derivation, in this discussion, irrelevant. So in this derivation, what we wanted to do was just to give a feeling about how the radiation comes about without going into mathematical details. Of course, if it's moving, if after the acceleration, if it starts moving with close to the speed of light, so of course this derivation will not be valid, but you have the derivation in your notes. Okay, let's give a break, and then after 10 minutes we can continue.